Okay, we are recording now. Okay, maybe we'll wait for 30 seconds and then get started. I hope you are making progress on the MP with Wi-Fi localization. Um, it's not a difficult MP, but more you play with it, you'll see there might be interesting room for improvement. So play with it. Okay. As usual, if you can turn on your videos, much appreciated. That helps. Um, Especially getting some visual feedback as to when something I said was not clear. In a physical classroom, it would be much better. But yeah, if you can turn on the videos every now and then, appreciate it. Okay, so let's get started. Um, we are talking about localization. We started with GPS, then we talked about Wi-Fi, and all along the way, as we are talking about these different applications, we are also hopefully getting clarity on various mathematical underpinnings, various algorithmic concepts, insights along the way. And this is going to be the flavor of the course. We're going to look at applications and we're going to say, look, here is the connection between the application and the math or the algorithm. Okay. So we did GPS, we did Wi-Fi, and we did Wi-Fi with this fingerprinting mechanism. And we said, look, there are lots of problems over there because uh, essentially with multipath, your received signal is a sum of many echoes. So you cannot really use the signal strength as an indicator of location because there are too many bouncing signals and your signal strength is not going to be nicely correlated. But it has some correlation. It's not that if you go far away, your signal strength will become higher. If you come very close to the Wi-Fi access point, your signal strength will degrade dramatically. That can happen in some corner cases, but mostly there is some correlation. So further you go, the weaker the signal, the closer you are, the stronger the signal. And Wi-Fi radar kind of systems um, exploited that and showed that, oh, some opportunity is there for localization. But in view of the limitations of signal strength based techniques, we said, look, let's look at another possibility, which is instead of trilateration, where we are trying to measure distance, we said, why not triangulation? And the idea over there is the Wi Fi access points should understand the angle from which the signal is coming from the user. It has nothing to do with signal strength, it's just angle. And if I know the angle from multiple Wi-Fi access point, this is what is called triangulate, which is different from trilaterate. Once I know those angles, imagine on a piece of paper, if you draw two straight lines from two Wi-Fi access points at theta 1 and theta 2, where the straight lines intersect, that should be the location of the user. So in preparation for understanding triangulation, again, the corresponding math/algorithm that we need to understand is what is called beamforming or angle of arrival. And that's what we started last class. And today the goal is, there's quite a bit of ground to cover today. So I'll try to move a little bit fast. Today the goal is to kind of finish up triangulation. So look at the math behind beamforming and angle of arrival. And then at the end, connect all of those and say, oh, this is how we actually do triangulation. And again, as throughout the course, these are only scratching the surface. There's a lot of work that has happened in triangulation and angle of arrival and beamforming. But I think some of these foundations would be enough for you to go and start reading and diving and digging into other things. Because without these foundations, if you go into some paper or some journal article, you may understand those at a high level, but you may not get what is happening inside. But I believe that with these foundations, you would be able to dig, explore all by yourself, because you know what the core building blocks are, or what the core insights are in beamforming and angle of arrival. Okay, so that's the context in which we are starting today's lecture. Any questions thus far? Okay, silence, I would assume, means you are following and no questions. Great. So let's quickly recap. We said omnidirectional antennas are like light bulbs. When you turn these light bulbs on, the energy goes in all directions, right? That's why it's omni. Whereas directional antennas, which is very high level term, is the idea where you direct the energy in certain, you direct more energy in certain directions and less energy in other directions. And the analogy for that is like spotlights or like flashlights, where you turn on the flashlight and the light kind of goes out in a cone in the main direction, and towards the side, some light leaks, but not too much. And this is essentially the notion of beamforming. Okay, and also we said that beamforming is essentially a spatial filter, because essentially you're letting energy go in certain spatial directions and you're regulating which way the energy should go and which way it should not go. So it's a spatial filter. And the way we are going to, there are many ways to design these beamforming antennas, and one way is basically what is called an array, what is called array processing. And the idea is we are going to use multiple omnidirectional antennas to actually make a directional antenna. Right? There are other forms of directional antennas where you physically put objects to guide the energy in certain directions, but we are going to look at the electronic way, the math way of creating directionalism in these antennas. Okay, and we started off by saying there's a linear array, there could be circular arrays, and that's what we said is there in Alexa. And we said, let's say all these antennas in a linear array transmit signals, omnidirectional signals. And we said that if you take a nearby location, at every location, the signal will be different. So you cannot really say much about any pattern of this signal at different locations nearby. Every location would have a different signal. So there's no real nice pattern. And that's what we call near field. And we said, look, we are not going to talk about near field today. There's good amount of stuff to talk about near field, but we're not going to talk about it because in most of the applications we are going to look at, where let's say this is your Wi-Fi access point, which has a whole bunch of antennas. The distance between these antennas is very small. So when you are sitting in your couch or in your living room, you are very far away from the Wi-Fi access point. So compared to the distance between antennas, that distance versus the distance that you are away from the Wi-Fi access point, it seems like you are very far from the Wi-Fi access point compared to this antenna separation. And that's called far field. And the main point we said is once you think about far field, the signals that are going from the antennas or coming from the antennas to your device, those signals are almost parallel. Right? And this is essentially the notion of far field, that the signals that are coming are almost parallel. And when can you say things are parallel? Exactly when the distance from the location to the antenna, that distance r, is much less than the distance, much greater than the distance d, which is the antenna separation. If that holds true, then as you can say, cos theta, this theta, or you can do in trigonometry, when this value is large and this side of the triangle is long, then these two sides almost become equal, and that's when they become parallel. Okay? So in far field, we are going to talk about the far field, and we are going to assume that in the far field, the lines, the signal directions are parallel. Okay? And that's going to allow us to see certain patterns of signals far away based on where you are, what your location is along theta. So as you go in different directions, different thetas, where by theta I mean this theta, as you go in different thetas, we will see that there is a pattern in the signal that you receive or transmit. Okay? Good. So let's get started. That's where we were last class, and let's get started here. Okay. Let's take the case where you want to transmit signals from your antenna array over here. You want to, this is your Wi-Fi device, right? There are many antennas. Okay. So in your antenna device, your Wi-Fi device is now trying to transmit to a receiver that is far away. And this receiver is essentially going to receive all these signals, but the signals are going to be almost parallel. Okay. Now let's say all antennas transmit the same signal, just for simplicity. Oh, by the way, guys, I hope you have the pre-notes. I think I uploaded the pre-notes. I uploaded the pre-notes yesterday night, but I made a small change and I uploaded again today morning. So if you can maybe download today mornings, but if you don't, if you've already started writing on your pre-notes, don't worry about it. It's a small change. In fact, it's just one additional page with a picture, so you can later copy the picture into your notes. Very good. Okay, so let's assume all antennas transmit the same signal. Let's also say that the RX receives signal S0T from antenna A0. Okay, so A0 signal, let's say, is S0T. A1, antenna A1 signal is S1T, and so on till antenna AN-1 signal is SN-1T. Okay, so these are the signals that are coming from each of the antenna elements. Oftentimes these are called antenna elements. Okay, so now what is the received signal YT? The received signal that the receiver receives is nothing but the sum of all these signals. Agree? So received signal is nothing but sigma I equals 0 to n-1 SIT. Very simple. And this is what the receiver receives. Okay. Now let's assume LOS path, which means there is no echo or multipath. So this transmitter, this Wi-Fi transmitter and this receiver are like in space, in deep space, right? So there's no reflection, nothing. Or maybe in a very big open field and they're floating in the air, so there's hardly any reflection. Okay? So we're only going to assume line of sight paths. Okay. Now the question is, I want to ask you this. If that is so, if it is line of sight path, then what is the difference between S0T and S1T? Remember, antenna A0 and antenna A1, they're both transmitting the same signal. The receiver receives S0T from antenna 0 and S1T from antenna 1. The question I'm asking is there any difference between this signal and this signal? Any thoughts? Do you think there's going to be any difference between the two? Are these, when the receiver samples these signals S0T and S1T, do you think the samples are going to be identical?
No.
Or is there going to be some difference? Okay, fine. I don't know if you're shy. Mohammed, if you're saying something, I don't think I hear you.
If there is some maybe difference in the distance.
I don't hear you, Mohammed, but that's okay.
Oh.
Now tell me this. Oh, you can hear him. Hey, can one of you talk so that I see? Can one of you talk?
Hello.
Oh, now I can hear. So Mohammed, can you say whatever you're saying once again?
Yes, can you hear me now?
Yes, now I can hear you.
Oh, okay. I was just saying that maybe there is some variation in the distance from antenna and the receiver.
Exactly. Okay. Look at this. the distance that the two signals travel has some difference. What is that difference? Now look, the two signals are parallel, right? So now let's draw this line. Okay, the receiver is here. Okay, so if when the receiver receives the signal, this distance and this distance, actually let me draw that with this distance and this distance should be same because they form a rectangle. Right? They are parallel, so they form a rectangle. So antenna A0 signal travels this much more than antenna A1 signal. Do you see that? Right? So the question is how much more? Or rather, antenna A1 signal travels this much less compared to antenna A0 signal. How much is this? If the receiver is at an angle theta, then how much is this value? Someone? Given that this is D, this distance is D, how much is this value?
Cosine theta.
Right? This is D cos theta. So we can say that S1T travels D cos theta less distance than S0T. Any problem? No problem, right? Very, very simple. Right? Very good. Now if I say, look, A0 and A1 both are transmitting the same samples, right? If A0 is transmitting A, B, C, D, or if A0 is saying, hello, how are you? A1 is also saying, hello, how are you at the same time, right? But when the signals arrive at the receiver, A0 signal arrives later than A1's signal, right? So when A1's hello or how has received the receiver, A0's hello is received by the receiver. Is that clear? Okay. So the question is, how much phase shift phi does this d cos theta distance cause? And that is not hard to calculate. But for that, we need to know what that frequency is. If the frequency or if the wavelength, we remember, right? That wavelength C equals F lambda, right? So the phase shift will depend on the frequency of the signal or the wavelength of the signal, right? So for instance, if this d cos theta, okay, let's not say d cos theta. If antenna A0 travels lambda distance more compared to A1, lambda distance, what should the phase difference be at the receiver? Lambda distance should cause a phase difference of 2 pi. Why? Imagine you're sending a sine wave. You are sending this signal. I am also sending a sine wave. But your signal travels lambda distance more, right? So this is yours. This is mine. So when this sample arrives at the receiver, this sample arrives at the receiver. Does that make sense? Right? Because your signal is traveling lambda distance more. Right? So if you think of phase, you are 2 pi behind me because it's traveling lambda distance more. I hope it makes sense. Okay. So lambda distance more causes 2 pi phase shift. But in our case, A0 travels d cos theta more, not lambda. So d cos theta distance causes 2 pi by lambda times d cos theta phase shift. Do you agree? I don't know, this is 6th standard arithmetic, right? So now, so now you see that when the difference between S0 and S1, the difference between S0 and S1 is that S0 is at a phase lag of 2 pi by lambda d cos theta, where the receiver is located at some theta from the transmitter. And what is the whole goal that we are trying to find? We are trying to ask, the question we are asking is, if the transmitter antennas send the same signal, what signal will the receiver receive if the receiver is located at a theta angle? That's what we are trying to find. That's our end goal. And for that, we have first characterized what is the difference between the signal S0 that comes from antenna A0 and S1 that comes from antenna A1. Very good. Okay. So now how can we mathematically write that S12 is nothing but S1T is nothing but S0T phase shifted by this phase phi, which is 2 pi by lambda d cos theta. Right? S1T is S0T phase shifted by phi, where phi is 2 pi by lambda d cos theta. Make sense? Very good. Maybe I can quickly draw this. If this is, or think of it this way. S0T is what the receiver received, and let's say that is or actually maybe let's make it easier. Let's say S0T, what the receiver is received is hello, how are you? S1T is basically, or at the same time if I write, S1T is hello, how are you? Right? And this phase shift is basically 2 pi by lambda d cos theta. Right? Another way of looking at it is, this is S0T, this is S0T, and S1T is basically the same thing, but this sample comes here. Right? S1T is 2 samples ahead. It's not 2 samples ahead, it's 2 pi by lambda d cos theta ahead. Good. I hope this makes sense. If not, go back to Fourier transform and think about how, when you shifted signals by samples, it actually corresponds to phase shifts. Very good. Okay, so then recall phase shifting is equivalent to shifting samples of the signal. So how do we write the fact that one signal is a phase shifted version of another signal? Well, phase shifting is nothing but shifting samples. So let's say S0T is cos 2 pi F1T. Then S1T will be nothing but cos 2 pi F1T plus phi. Right? This is phase shifting, right? Where phi is this 2 pi by lambda d cos theta. And then we saw, remember in FFT property, we said shifting a signal is the same as multiplying e to the power j phi to the FFT of the original signal. Right? So shifting S1t can be written as S1f is S0f multiplied by e to the power j phi. Does that make sense? So now we have a relationship between the two received signal from the two antennas. Right? Very good. And with this relationship is in the frequency domain. Right? In the frequency domain, we know what is phi. Phi is 2 pi by lambda d cos theta. We just multiply e to the power j phi to the frequency domain representation, and we have S1f with respect to S0f. Very good. So now let's write out all the signals S1, S2, S3 all the way till Sn minus 1. This is Sn minus 1. Okay. So S1 is nothing but S0 e to the power j phi, where phi is 2 pi by lambda d cos theta. Now guys, what is S2? S2 is this signal. This one is S1, S0, this one is S1. What is S2? What is the relationship between S2 and S0? That relationship is basically S2 travels this distance less than S0. You agree? How much is this distance? The antennas are all equispaced. Guys, how much is that distance?
2D cosine theta.
2D cos theta.
Perfect. So this is 2D cos theta. Now tell me, S2 is S0 times what?
E to the power j 2 theta, 2 phi.
Perfect. E to the power j 2 phi. Okay. Sn minus 1 is S0 e to the power j n minus 1 phi. You're happy thus far, right? There's no surprise anywhere. Right? Very good. Now what is y in the frequency domain? Y is nothing but, again, I'm going to add things up. Adding in time domain is the same as adding in frequency domain. Right? So I'm going to say, let's say k equals 0 to n minus 1, S0, e to the power j, k phi. Does that make sense? Just for clarity's sake, let's write S0 is nothing but S0 e to the power j0, which means S0 is S0, right? We are looking at every signal with respect to S0. S0 is what has been received by the receiver from antenna A0. We don't know what the transmitter is transmitting, right? We received one signal from A0, antenna A0, and we are trying to see the other signals from the other antennas. How do they differ relative to that S0? I don't care what that S0 is, right? Very good. So now when you do this, when you expand, when you write this out, it will turn out that this value, right-hand side, turns out to be S0 times 1 minus e to the power j n phi divided by 1 minus e to the power j phi. You don't have to worry about that. This is a nice approximation for a closed form. But what we are interested in is if this is the signal that the receiver receives, right? Now I can plot this signal with respect to phi, but phi is a function of one-to-one function of theta. So I can plot this signal y with respect to theta. You agree? That means now I'm seeing for a receiver, as the receiver is at different thetas with respect to the transmitter, what does the signal look like? Okay. And then we see that when we plot it, we'll realize that the signal would look like this when n, which is the number of antennas, equal to 2. Okay. When n equals 4, the signal looks like that. And when n equals, let's say, 8, the signal looks like this. Oops. Come on. So what does that mean? It means when you take theta equals 0, what is theta equals 0? This is theta. Okay. Sorry. When you take theta equals 90. Yeah, maybe I should have drawn it. Maybe I should have done this. Okay. When theta equals 90, that is where all the signals are maximum. Oops. In other directions, other thetas, the signal becomes smaller and smaller. Interestingly, when you have n equals 4, 2 antennas, as you take more and more antennas, your sharpness of the way you're guiding energy changes. And not only that, there are also certain directions in which the signals cancel each other along all locations in that direction. So if you take a location like this one, let's call this theta 5, just arbitrarily, let's call this theta 25. Okay, along those directions, the signals will actually be attenuated. So if you use this kind of an array, in the frontward direction, you're going to see most of the energy, but there'll be some directions in which you will see less energy. And again, some directions will be more energy, right? So I hope this is clear to you what this means. This is often called the radiation pattern. This tells you how much energy goes along what theta. Make sense? So now if you look at the pattern of the beam corresponding to these radiation patterns, then it would look like this. If this is the transmitter in the center, this is the transmitter in the center, the red dot, the beams, or it's actually that the signals would get radiated, but in certain directions it will cancel out. This is when n equals 2, this is when n equals 4, this is when n equals 8. In certain directions the signal would add up, in other directions the signal would cancel out, because the math is saying so. The math over here is saying so. Right? And this is at the far field. This is not going to happen in the near field. So if you now ask the question with n equals 2, how much signal do I get at some theta? Let's say this is the theta. The answer is you're going to get this much signal. right? Because that value tells you how much the signal added up on top of each other in that direction. If you ask the question, how much signal do I get in this direction, where that is the theta, the answer is very low. It's almost canceling out. Right? So depending on which direction the receiver is, the signal that the receiver would receive would change. And as you increase the number of antennas, this beam will become sharper, and there will be these flowery petals. And the names given to them is that this is called the main lobe, and these are called side lobes. Questions? And also the other thing to observe is that things are symmetric along this line on which the antennas are placed. Why? If the signals add up constructively in front, they will also add up constructively at the back, because the phases of the signal, the d cos thetas, are same on both sides, right? Do you see that? I hope you see that. This is antenna. If this is the receiver here, and the difference between the two paths is d cos theta, that is going to be the same thing in this direction as well. So whatever this receiver gets, receiver number 1, this second receiver will also get exactly the same. Because the paths to receiver 1 and receiver 2 are both have this difference of d cos theta. And that d cos theta will lead to the same phase difference. And that same phase difference is the reason why signals are adding up constructively or destructively or somewhere in between. So basically, summary is, because signals are traveling different distances, they are phase shifted. And when they're phase shifted, depending on how much the phase shift is, they may be adding up fully constructively, which is giving you a main lobe. They may be adding up totally destructively, which is giving you what is called a null. This is called a null. And they might be adding up somewhere in between, which is called a side lobe. Okay. So observe that the natural beam is pointing towards front and back. Or natural main lobe beam. So someone quickly tell me, why is the main lobe pointing front and back? Why isn't the main lobe pointing at some theta? Go ahead, Eric.
Is it because all the signals are parallel?
It's because all the signals are parallel. So what do you think is the phase shift along this direction? This should be like vertical. Okay, it's a little bit crooked, but think of that as vertical. What do you think is the phase shift between S0 and S1 in this direction?
0 almost.
0. What is the phase shift between S0 and S2 in that direction? 0. So it's like the two signals have 0 phase shift. So when they come to the receiver, they're adding up on top of each other. That's where you're getting the high signal. Right? In other directions, in this direction, there's some other phase shift, 2 pi by lambda d cos alpha. And at that phase shift, the signals are not adding up on top of each other. There is some gap, there's some staggering, and therefore when you add up with stagger, this value is less than this value. That lobe, that range, that gain is low. Very good. Question? Okay. So now suppose I tell you.
Oh, sorry.
Yeah.
Can we always guarantee that the antennas are actually equally distant?
Yeah, we cannot. That is why there's all kinds of calibration and all kinds of stuff that happens with antennas, right? But you realize, right? If the distance between the antennas is large, right? Then a little bit of error in antenna placement doesn't matter, right? But if the distance is small, and if lambda wavelength is small, right? Then that distance becomes more and more important. So you have to manufacture the antennas with very high precision and all of that. We are not going to get into those hardware details, but very much relevant. Your question is very relevant. That's why there's a lot of work on calibration. Because even if the manufacturing, if the factory says this antenna has equidistance of D, that may not be precise, right? So you need to now calibrate by maybe looking at the signal and then figuring out, you know what, actually it's D plus epsilon, and this is how much the epsilon is. So there's all kinds of calibration that happens. Does that answer your question, Eric?
Yeah.
Yeah, good. Okay, so now I have a question for you. This antenna main lobe is always pointing towards the front and back. But suppose your receiver is now directed towards the direction theta. So ideally what you should do is steer the beam, make the antenna beam like that, right? Because you want your receiver to get the most amount of signal power. So how do you steer this beam? One way is you take your Wi-Fi access point and you turn it theta, right? That's a possibility, right? But you don't want to do that. You want to electronically steer it. So give me an intuition on how I can steer this beam to now look at this direction. So I want all the signals to add up coherently. By the way, this is a new word I'm using. Coherently means right on top of each other, which also means constructively, right? So I want the signals to all add up coherently towards theta, even though naturally they add up towards 90 degrees in front. Someone was answering that question. Go ahead.
Yeah, you put the different phase to the other signal source.
Exactly right. You say, look, along theta, the signals all have some different phases when they arrive over there. So what I'm going to do is when I transmit the signals from the antennas, I'm going to compensate for each of those phases at the transmission time itself, right? So if antenna 1 travels d cos theta less, I'm going to change the phase at antenna 1 to make it d cos theta or phi more. So when that signal, which is getting transmitted from antenna 1, has a higher phi, when it travels less distance, that higher phi will get cancelled out and they'll all line up constructively at the receiver. Let's look at it, okay? So now I want the main lobe to point towards my intended direction theta. That is, maximize signal power towards theta. How? Oh, by making the signals from all antennas add up coherently or constructively in the direction theta. So let's first see how signals add up along theta. Recall that y is nothing but S0. Now this is in the frequency domain. S0 e to the power j phi. Phi is nothing but 2 pi by lambda d cos theta, right? Plus S0 e to the power j, sorry, not minus, j2 phi plus so on S0 e to the power j n minus 1 phi. This is what the signal is, right? That's adding up. And that is nothing but this. If this is S0, then S1 is this. S2 is this. Sn minus 1 is this. right? They're all phase shifted by phi to phi. So this phase shift is phi. This phase shift is 2 phi. This phase shift is 2 phi. This phase shift is n minus 1 phi. That's what is happening at the receiver, and the receiver is adding up all of these, and the receiver gets some value. That value is this value. That value is this value along theta. So let's just quickly write that. This is S0. This is S1. This is Sn minus 1. So very true. Now I want these signals to add up coherently at theta. So for max SNR at Rx, what should I do? I should shift each SI to compensate. Maybe I should write phase shift. Each SI to compensate for path delay it would experience. I hope this is clear. So what I transmit X, by the way, right? I don't transmit S, remember, right? I transmit X, but that signal, when it arrives at the receiver, it becomes S. Okay. If it's a line of sight path, then S is nothing but X divided by K 4 pi R square, remember, right? Received signal power and the transmit signal power. Okay. So what I transmit is nothing but X0 e to the power minus j phi, X0 e to the power minus j2 phi, so on, X0 e to the power minus j n minus 1 phi. What does that mean? I take this, whatever the signal that I transmit out of this antenna A0, let's call that X0. It can be any signal. I don't care. But at antenna A1, I transmit that same X0, but give it a phase shift of minus phi. Right? Because I know when this signal arrives at the receiver, this signal will get a phase shift of positive phi with respect to S0. So if it gets a positive phi, but if I give it a minus phi phase shift early on during transmission itself, those two will cancel out at the receiver. Right? So and now for the second antenna, I do minus 2 phi. The last antenna, I do minus j n minus 1 phi. And all of that becomes the following: S0 e to the power j phi. This is what the receiver, sorry, jk phi. This is what the receiver is transmitting. And that, when it goes to the, sorry, this is what the transmitter is transmitting. And that, when it arrives at the receiver, it becomes the jk phi. Does that make sense? Right? This is nothing but SK. I shouldn't say that. This is nothing but XK. I shouldn't say that. No. Don't worry. Tell me if this is right. Any questions?
I don't know if it's right, but it just in my head, I feel like on the figure on the left, the sequence should be reversed.
Why?
Because because when you drew the diagram above, and isn't it the one that has to travel a little bit longer is the transmitter on the left?
You're right. This diagram that I drew here, this diagram that I drew here should be the other way. It should be this, 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 and so forth. Do you see why? Because S1 is traveling less than S0, right? So if S0 is ABC, if S0 is sending ABCD, by the time A arrives at the receiver, S1's B has arrived at the receiver. So in other words, S1 is ahead of S0, right? Because S1 is traveling less. Jian, how does that make sense?
Yes, thank you.
Let me correct it, okay? Quickly. Wow, that's actually a good one. iPads make these things easy. You're right. Thanks for catching that, actually. Cool. And now you're basically giving it a phase shift of minus JK phi, which means you're basically staggering, you're basically giving this signal a phase shift ahead so that when it gets compensated, it will line up. So this means when you add things up, this becomes nothing but k equals 0 to n minus 1 as 0. Right? Because all these have cancelled out, which is nothing but n as 0 in the direction theta. Okay? This is called delay sum beamforming. Okay, why is it delay sum? Oh, you are basically delaying the signals and then summing it up. Very simple, right? So guys, if I tell you, you need to steer your beam towards direct angle beta, what are you going to do? Quickly tell me one line answer of what you should do. If you want to direct your signal towards beta, what should you do? You compute phi, which is 2 pi by lambda d cos beta. And then at your linear antenna, you basically put a e to the power j minus k beta on the kth antenna. That's it. Right? And that will align things up. Okay. So here is an analogy, right? Imagine there are multiple runners running on a circular field, track and field. You want all of these runners, suppose these runners all have the same speed. You want all of these runners to finish at the same time, right? When they end, they should all line up in a straight line and they all travel at the same, run at the same speed. But because these inner circle and the outer circle of the track and field have different lengths, right? You need to stagger them up front so that they end up at the same time. If you make them all start from the same location, they will end at different delays. And that is exactly what is happening in the antennas, with the antennas. Right? You're giving this minus e to the power j phi, minus e to the power minus j2 phi, e to the power minus j3 phi. You're giving this phase shift up front so that they end up exactly at the same time at the finish line. I hope that that analogy clears things up. So stagger runners at the starting line like phase shifts at antennas, at transmit antennas, to ensure they all run the same distance and end and finish at the same time. That is signals travel, that is signals add up coherently. Please ask me questions. I think this is a perfect analogy for what antenna arrays are doing.
How does like Alexa know the microphone away works, but it doesn't actually send out sound?
Yeah, we'll talk about this. This is exactly angle of arrival. We'll talk about it right away. But this was about transmitting. You have an antenna, you want to transmit. Your cell tower does this. I mean, it does not do exactly this algorithm. There are more sophisticated algorithms, but this is exactly what your cell tower does. Your cell tower says, okay, somehow cell tower figures out that your mobile phone is at angle theta. So your cell tower says, okay, I'm going to phase shift, stagger these signals in the right way so that most of the energy arrives at your mobile phone. And that way your mobile phone signal, SNR, or even RSSI is much stronger. So this is the transmission part, and this is called beamforming. Now let's look at the reverse, which is angle of arrival. Let's say your mobile phone sends a signal and your cell tower needs to figure out which angle the signal came in from. This is the same as you say, hi, Alexa, and your Alexa figuring out, your Amazon Echo figuring out which angle the signal came from. Because if I know that angle, I can beamform at that angle. I can transmit towards that angle. Right? So these are very kind of related problems. Okay. So in this case, the question is, let's say there is a transmitter in far field. The transmitter is transmitting a signal, and the signal is arriving at your array of antennas or microphones, right? So signal arriving from far field. An antenna array needs to figure out the angle of arrival, which is theta, which is also called AOA. This is also often called direction of arrival, DOA. Different papers and articles will talk about them as DOA or AOA. So the question we have on our table is, how can you estimate AOA? You're getting these signals on your antennas and you want to estimate which angle the signal is coming from. Well, the answer is kind of simple. It's similar concept as beamforming, right? So let's model this. So look, the received signal is now Y0, Y1, Y2, so on till Yn minus 1. This is coming to antenna A0. This is coming to antenna A1, and so on. Or let's maybe even draw it this way. This signal is coming here. This signal is coming here, dot, dot, dot. This signal is coming here. This is what you're receiving. Y0, Y1, Y2 is what each antenna element is receiving. So let's say that the signal that the antenna is receiving, just for simplicity's sake, is cos 2 pi f1t. This is Y0. Let's say the transmitter is transmitting a cos signal. Y1 is receiving some phase shifted value. right? Wherever the transmitter is, there's going to be some phase shift, and that phase shift is phi. And notice that phi and theta again has that relationship. Right? Now we are just doing things in the other way. The antenna is receiving as opposed to transmitting. So y1 is cos 2 pi f1t plus phi, so on, cos 2 pi f1t plus n minus 1 phi. Are you all with me? So this is what the antenna is receiving. The antenna array is receiving if the transmitter is sending cos 2 pi f1t. Now the transmitter might be sending something else. We don't care. So in the frequency domain, let's say that the first antenna receives XF. This is what the antenna is sending. Sorry, this is what the first antenna is receiving. So then I can write the whole vector yn as xf times e to the power j0, e to the power j phi, e to the power j2 phi, so on, e to the power jn minus 1 phi. I didn't do anything. It was exactly like what we did last time, what we did here. Now that I'm just modeling what is getting received. This is what I received in my first antenna, which is A0. This is what I received in my second antenna, at my second antenna. This is what I received at my third antenna. Okay, so one thing I should probably make clear is this is XF is getting multiplied with everything. You see what I mean, right? XF times e to the power j0, that's y0. XF times e to the power j phi, that's y1, and so on. Very good. So now the question is, from this received signal vector, how do you detect what is theta? You have received this. This is in time domain, but this is what you have received in frequency domain. Guys, are you okay if I write it this way? Right? So this is what you've received in the frequency domain. How can you say what is theta? The angle in which the signal is coming, or the angle in which the transmitter is located. So here is the answer. Do delay sum once again. Okay, so algorithm is as follows. For theta I, where theta I is the direction of the transmitter, I don't know that, but I'm going to search. So let's take theta I from minus pi to pi. I'm going to vary that. So for any given theta I, I'm going to calculate phi I, which is 2 pi by lambda d cos theta I. Okay, so in other words, if the transmitter was at direction theta I, then I expect that my antennas would have relative phase shifts of phi I. Phi I, 2 phi I, 3 phi I, 4 phi I, n minus 1 phi I. Make sense? So now what I would do is, I would correlate, meaning I would take I would take these signals y1, y0, y1, so on till yn minus 1, which is what I received from each of my antennas. And I would take each of these signals and stagger them by minus j minus j how much? Alpha I minus j2 alpha I dot 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 minus j n minus 1 alpha I. Hey guys, what am I doing? And that's it. And I will call that C theta I. That value, I will call that C theta I. And I'll repeat this loop for all values of theta I from minus pi to pi. Ask me questions if it's not clear. Okay, let me tell you the analogy first. Now the problem is the runners on that track and field event, they're starting with some unknown staggering. You don't know that, right? All you know is when they're finishing, you are seeing what is the gap at which they are finishing, right? If they start at some unknown stagger, does that make sense? The transmitter is transmitting from some theta, which means the signals are coming with some stagger. But I cannot see that stagger because the signals are mixing. Actually, the right analogy is this. Imagine this track and field. So this guy, so now instead of one runner, imagine a train of runners. Okay. If it is one runner, the problem is simple because if then they are staggered, then at the finish line, they will also arrive with the same staggering. If these guys are staggered, then when they arrive at the finish line, this guy will also, all these guys will arrive with the same staggering. So you can observe the staggering and say, what was the original staggering? But instead of that, imagine there are lots of people. These are the signals that the transmitter is transmitting. So when you observe at the finish line, you are seeing all these signals are adding up. Right? So when you're watching them, you're seeing all these signals adding up. So you do not really know what the stagger is. Question. I don't like the faces that I see.
So are you basically like delaying the signals so that they basically line up when they
Exactly. Whatever I receive, I am delaying them with different values and adding up. If the way I am delaying them is correct, right, that means I've compensated for the actual signal's path delays. If I do that correctly, then the add up will be a coherent add up. But if I delay them incorrectly, then the adding up will not be coherent. So this C theta I will be large when I have picked the right value of alpha I. And it will be small when I have picked the incorrect value of alpha I. Okay. So I'll run this for loop, and at the end, I will plot C theta I versus theta I. I'll plot that. And that spectrum would look like this. This is theta I. This is C theta I. And look, guys, this is essentially correlation. It's a dot product, right? So when, oh, there's one more thing I should say. This should be a conjugate. No, actually, sorry. I've already done minus. It's okay. It's okay. So when this exactly compensates for the signal path, that will be this theta I, this theta star. And that's when you say AOA is theta star. Done. Right? For other values of theta, the correlation will be small. Why? Because when you have delayed the received signals, you did not delay it in the correct way so that the signals that you received did not add up coherently. And this is what I was trying to say with this analogy as well. When you're observing the finish, you want to delay them and you want to see if upon delaying them, do they add up very nicely? Questions? If it does not make perfect sense, please go back and ponder on this. All you're doing is you have 5 antennas, you have 5 signals. You're delaying the first signal by some value alpha I, delaying the second with 2 alpha I, delaying the third with 3 alpha I, so on. And then you're adding up all the 5 signals from the 5 antennas. And you see how much the add up is. The point is, if you got the right alpha I, then all these added up values would be very high because you've essentially compensated for the path delays that the signals experienced. If that is clear, now let's assume this. Let's assume multiple transmitters. Sending in parallel. Can we still decode the multiple AOAs? So here is the case. I have multiple antennas. One transmitter is transmitting the black signals from some angle theta. The other transmitter, transmitter 2, is transmitting the blue signals from some transmitter psi. Okay. So what do I receive? I still receive Y0, Y1, Y2, so on till Yn minus 1. I still have n antennas. I receive n signals. But now these signals are essentially an addition of the transmitter 1 signal and the transmitter 2 signal from different angles. So let's say transmitter 1 signal is x1 and transmitter 2 signal is x2. So what I receive is actually x1 coming from some angle theta, and let's say 2 pi by lambda d cos theta is phi 1 and 2 pi by lambda d cos psi is phi 2. So if it's coming from theta, the phase shift is phi 1. If it's coming from psi, let's say the phase shift is phi 2. Okay. So then what I receive is nothing but x1 times e to the power j0, e to the power j phi 1, e to the power j phi 2, so on, e to the power j n minus 1 phi. Sorry. And tell me if that makes sense. Like we said, when we do matrix multiplication, this times this column plus this times this column. This times this column is nothing but what the antenna is getting from transmitter 1 plus this times this column is what the signal is from transmitter 2, and the transmitter, the received signal, what the receiver is getting, the received signal is this transmitted signal plus this second transmitted signal. That's clear? Good. So then we can write y as nothing but as, where y, this is the array output. A, this is called the steering matrix. And S, this is called the source signal. Any questions? Please feel free to ask.
So what would the AOS spectrum for multiple transmitters look like?
Oh, we haven't gone there. We are still setting up the problem. We are saying if there are multiple transmitters, we are still going, the receiver is still going to receive this array of signals at different antennas. And God knows that the oracle or God knows that this actual signal that you're receiving is nothing but the sum of the two signals that are coming from different directions. And we are essentially modeling that in reality, it is the first transmitter signal phase shifted by theta, the phi coming from theta, plus the second transmitted signal phase shifted by phi 2, and where phi 2 is a function of psi, where psi is the angle of arrival. So we've set up the problem, and the question is, now how do you figure out theta and psi from this received signal? Okay, we have set up the problem. You know, this is the thing about solving problems with models, meaning I don't know the answer, but let's set up, if this was how it was happening, what should my measurement look like? Right? You set that whole thing up, and then you figure out how to solve that mystery. Very good. Okay. So now how can you decode theta and psi? Okay. This is psi. You want to decode theta and psi from this vector y0, y1, yn minus 1. That's really your goal. Okay, good. Answer, you look for a certain phase pattern. So correlate. What phase pattern are you looking for? You say, look, if there is a transmitter at some theta direction, I know what the corresponding phase shift should be. So let me take my signals and phase shift in the opposite directions. Okay. So I would give a phase shift to my signal as follows: e to the power j0, e to the power minus j phi 1, e to the power minus j phi 2, sorry, minus j 2 phi 1. Times. So, okay. So if I multiply my received signal with this vector, this is like delay sum, right? This is delay and summing. Why? Because I'm delaying each of these signals. Oh, I should write this as y0, y1. Hey guys, are you all clear that this is nothing but delay summing? Can I get some more yeses? Unmute if you can. Can I get some more yeses that this is nothing but delay summing? Okay, good. So if you now delay sum this, that is the same as delay summing this, right? You don't know what this exactly is, but when you're multiplying something with this left-hand side, you're actually also multiplying something with this right-hand side. So you can write that as e to the power j0, e to the power minus j phi 1, e to the power minus j n minus 1 phi 1 times this whole thing. Are you with me? I've not done anything fancy. Okay. So now look what happens. Of course, you perform this for all values of phi I. Right? You're basically delay and summing the received signals with different values of phase shifts. And you hope that the dot product is large when AOA phase matches phi I. In other words, what are you doing? Two signals are coming from different directions. You are giving phase shifts to that signal to compensate for the delays caused from one of the signals. So one of the signals is adding up coherently, but the other signal is not adding up coherently. But the hope is one of the signal adding up coherently will still give you a bump in your correlation value, in your C theta value. Right? And again, when you give a different phase shift, the second signal will get delayed and summed, will add up coherently. The first won't. And again, it will be a bump. But when you're giving a phase shift that does not coherently align the first one or the second one, hopefully the correlation value would be smaller. And you hope that you see two peaks in your AOA spectrum. Two peaks. That's the hope. Now, if that is not bad enough, right, with already two signals, you become worse. So guys, your AOA spectrum, will it become better or worse with more number of antennas? Anyone? Anyone? See, with more antennas, you will have more signals coming from each transmitter, right? So when you compensate for those phase shifts, you will add up many more, you'll add up more signals, right? And that will give you a bigger bump because the other guy's signals are kind of getting randomly offset by your phase shift, by your delay. So more the number of antennas, your peaks get sharper. Your AOA spectrum peaks get sharper. Okay, good. So now to make things worse, in reality, there is actually also noise. Which means, now look, instead of writing this vector, I'm going to write that as, to simplify, A0, or sorry, A1, A2, AD. Can someone tell me what this means? What is going on? How many transmitters are there? How many transmitters are there?
D transmitters.
D transmitters. Okay, so now we are generalizing. So D transmitters plus there's some noise vector. How many noise vectors? Guys? How many? This vector that I'm writing right now, what is the dimension of that vector?
D.
Ah, I caught you.
Oh, shit.
Because this noise is getting added to every antenna. I hope you see the structure of this equation very clearly. D signals coming from D directions, adding up, that gives you an n-dimensional vector. But with the signals, you're also adding noise at each antenna. So these together give you the final n-dimensional vector at the receiver. Is it difficult? I see Deep and Anthony's face does not give me confidence, but thank you very much for keeping the video on. Do you?
I think it makes sense to me.
Huh?
It makes sense to me.
It makes sense, right? If you got this one, sorry, if you got this one, then this is nothing but the same thing. Instead of 2 transmitters, I made D transmitters, and I just added a noise to the antenna signal. Very good, right? Now, if I want to figure out AOA, what I do is I figure out the phase shifts for different directions. Let's call it AI. And remember, right, you have to multiply with minus j, right? If the signals are coming with j phi, when you multiply, you have to multiply it with minus j, and that's why I'm putting this conjugate here. Plus this is what I'm doing with the received signal. And that is what is happening actually. Because this is reality on that only God knows. You don't know. You only know this. But God knows what is inside that Y0 signal that you've received. So when you multiply the left-hand side with this, God is multiplying the right-hand side with this. Right? Now let's say this is north. This is west. This is south. Those are the directions from which the signals are coming. When your AI also has the same phase shifts as north, then these two will be the same vector, just conjugates of each other, right? When AI is north. So this multiplication would cancel off, and you would end up adding all these signals. Sorry, you'll end up adding all the signals in X1. Coherently adding, right? So if you work out the math, it will essentially be AI squared, because that is AI squared is nothing but this times this. I'm again going to go back to A1, A2, A3 just for math's sake. plus AI AJ sigma j equals 0 to n minus 1, j not equals I. Let me move this. Times xj plus AI n. I'm going to say this, but you have to spend time on this at home. When your AI is correct, means aligns with one of the angles from which the sound is coming, the signal is coming, then you get an AI square term because this AI matches with one of the angles in which the signal is coming. So that becomes AI squared, right? That term hopefully is positive. Not hopefully, this term will be positive and large. But these terms are where the signal is coming from some angle which has some phase shifts, but you're giving a different phase shifts to the signal, so they are not coherently adding up. So this is hopefully small. This is positive and large because it's coherent. This is hopefully small because it's incoherent. And this is also hopefully small because noise is random and you're giving it some phase shifts, it is going to remain random. So this is also incoherent. Okay. So by correlating along all directions AI, we get an AOA spectrum. Right? Your AOA spectrum essentially should have peaks at where your AI is correct, right? And everywhere else, there should not be any peaks, right? So ideally, your AOA spectrum should look like this. And then you know, this is the one angle in which one transmitter is there, and this is the other angle in which other transmitter is there. But in reality, if you have these two, you will get the sum of them. So what you end up getting is really this. This is the sum of black plus blue. And that is where with many, I mean, if you get lucky, if the two angles in which the signals are coming and are very far apart, then it will be like then the sum of those two would be pretty good. The sum of those two would be like that. Then you can still decode the AOA. But if the two signals come close by, like this, then you might actually end up getting a much less sharper peak, and the peak might be in the wrong location. Right? Because two peaks are kind of getting added up. So remember, as the angle of the arrivals become closer, you get smudged, the peaks get smudged. But the way to cope with that is either increase the number of antennas, that will give you more resolution, or design a better algorithm, which is better than delay and sum. Okay. So again, one way to look at this as an analogy is you have one team that has some stagger, and you have another team that has a different stagger. Let me write this with a white. You have another team which has a different stagger. And now they're all running in. And if you take this team, if you take these guys, this is your antenna 1 or antenna 0. This is your antenna 1. This is your antenna 2. This is your antenna 3. So if you take these guys and you stagger in a way, you stagger the right way, all these guys will end up adding up coherently. So you should get a peak. And then if you take these guys and add a stagger, which is proportional to this, then these guys will add up coherently, but these guys will not. I definitely want you to think about this at home as to why at the receiver, if you delay and sum, you might be able to pick up one, you might be able to pick up other, but in cases where they're close to each other, you might have a wrong value of theta. Okay, we are pretty late today. There's one last slide that I had which talks about a very different kind of an algorithm, not delay and sum, but maybe I'll quickly finish talking about it for the first 10 minutes next class and then move on, because I feel like you need to absorb this very well. Of course, this is a very different algorithm. We are going to call this music. And this is an algorithm where we need to understand a little bit of the eigenvectors and eigen decomposition that we talked about earlier, right? But I first want you to completely absorb delay and sum very well for both transmitting and for AOA, angle of arrival, and especially what happens when there are multiple signals. But the whole idea is, I don't know what the angle of arrivals are, but I'm going to try different angles. How do I try different angles? I phase shift the signals corresponding to the phase shift from those angles, right? And I try for different angles with different phase shifts, and I try to see if it coherently adds up or not. Okay. Definitely, I want you to look at this. I think there'll be an MP around AOA, so you'll get a chance to play with it once again. But you don't want to have a hole in this, particularly because once you get it, it will be very, very clear. It's one of those things that just clicks and everything is clear, right? All the math should be clear. Questions? Questions?
How does this change if we were to model in like 3D, right? Does it like is it still just theta, or
no? Then you need a 2D array of antennas.
Okay.
Right. So your beam can steer in any direction, and you'll have two angles. One is called azimuth, meaning the horizontal plane, and the other is elevation, which is the vertical plane. Right? So anytime an angle of arrival, you are going to basically estimate the azimuth and the elevation. So your antenna array is going to look like this. Right? And your beam would be like that, and that beam would have an elevation. And on the 2D plane, your beam will also have, if this is, let's say, north, your beam will also have azimuth theta. So azimuth will be theta and elevation will be alpha. And your beam will steer. By the way, all these self-driving car, radars, even some kind of LiDARs are of course light, but the core principle is you are basically steering the beam in different directions and seeing the reflections of the signal, and from that you're figuring out the image in your environment. Right? You're figuring, for example, depth cameras, right? They're shining a signal, looking at the reflection. Now you can shine the signal in different directions and look at the reflections in different directions. And from that you can figure out, oh, this is the 3D model of the environment I am in. So radar, weather radars, LiDARs, self-driving cars, many, many applications of these kind of beamforming. Okay, we'll stop here, but if you have questions, hang back and we can chat about anything. But otherwise, I'll see you on Wednesday, and please finish up your MP, and more MPs coming around these kind of beamforming stuff. Questions? Okay, today I was a little bit heavy maybe, but I'm hoping you guys would go back and look at this. Please do look at this.
I noticed that there's an array track paper that is linked to today's lecture. Do we just have to like read that?
Yeah, we'll assign that next lecture because array track is related to this music algorithm. So I'll assign that next class.
Cool. Okay.
Okay, thanks guys.